Hello and welcome. Today we're doing a quick review on aromatic reactions. We're mostly focusing on electrophilic aromatic substitutions, and this is presented to you by Science Visualized. So for example, here we have a question that says provide the products. Now, when you're looking at question A, you have an aromatic compound with a methyl group and a methoxy or alkoxy group. Both of these are ortho-para directors. That means they'll direct an incoming group to the ortho and para positions. So if you look at the reagents, we are using bromine and FeBr3, and that gives a bromide plus electrophile. So that's a new group that we're adding to the ortho and para position. Now, if we focus on the methyl group, that one, it will direct a new group to the ortho position. So we have two ortho positions, and to the para position. Para is 1,4 with respect to that side group. And then if we look at the methoxy group, this one here, it's also an ortho-para director, so it directs a new group to the ortho with respect to the methoxy group. So that one, those are the ortho, and then also to the para position, which is that one there. Now this position here is hindered because it's between the methoxy and the methyl groups. And because of that, we're not going to add any group there. So no group adds there. So that leaves us with only two options. We're going to add the new groups to this position and that position because both directors agree. So that means the first product will have the new group, which is a Br electrophile, added to that position. And then the second product will have the Br added to the other position. Question B. We again have a methyl group that's an ortho-para director. So ortho. The next ortho here is blocked because it already has an OH group, so nothing adds there. And then para with respect to the methyl group. And then for the OH, it's also an ortho-para director. So that's ortho with respect to it and para with respect to it. So now we see that these two groups do not agree. But actually the OH is a stronger, so OH is a stronger director than a CH3, and because of that, the OH wins, and therefore we're going to add the new groups to that position and that position. So you end up with I plus, remember I2 and copper chloride gives you I plus electrophile, which will add to that position and to the other position. And those are the two products formed. Number C. This reaction is called Friedel-Crafts alkylation. Friedel-Crafts alkylation reaction. And basically what happens is you start with an alkyl halide, so that's an alkyl group, and the halogen in this case is chlorine, with aluminum trichloride. You end up generating a carbocation at that position where the halogen was connected, and that becomes the electrophile that will add to the aromatic compound. Now, if we look at the methyl group, we know that's ortho-para director, so the new group will go there. We've said that it cannot go there because that position is hindered, and then to the para position. The other group has a carbonyl, and therefore that makes it a meta director, so it adds to the meta position, which is here. Now we see that these two groups do not agree, but always ortho-para wins against meta. So ortho-paras are electron donating groups, while meta directors are electron withdrawing groups. So electron withdrawing groups deactivate the ring, electron donating groups activate the ring, and therefore you end up adding the new group to that position and that position. So the product will be the new group added to that position and that position. Remember, the new group is this electrophile. Number D. Now we have NO2, that's a meta director because it's an electron withdrawing group. And here we have an alkyl group, that's an ortho-para director. And ortho-para will be ortho to this position. So that's the ortho position and para position. While the NO2 is meta director, so meta and the other meta is here. So basically, those two groups agree, and therefore the new groups will be added to that position and that position. Now, when you look at the reagents, we have acyl halide. So acyl iodide in this case. Halide is a general name, where you have a halogen at the acyl position, then you have a carbonyl, and that requires aluminum trichloride catalyst. When you mix those together, you'll generate a psyllium ion. So plus like that, which is stabilized by resonance, where you can actually delocalize the positive charge to the oxygen, and you end up with triple bond like that with a positive on oxygen. And because it's stabilized by resonance, that becomes a very stable intermediate compared to a carbocation, and therefore there will be no rearrangement. So that's a group that we're adding to this position and that position. So the product will have the acylium or acyl group added to that position, and the other one will have the acyl group added to this other position. And this is called Friedel-Crafts acylation. This is preferred to Friedel-Crafts alkylation that we saw before, because alkylation has a carbocation intermediate which can undergo rearrangement. Question E, we're starting with just a benzene ring and reacting that with aluminum. We're reacting that with alkyl halide, so this long alkyl chain, and then the halogen in this case is chlorine and aluminum trichloride catalyst. What ends up happening is that you end up generating a carbocation at that position, and that's a primary carbocation which is not stable, and because of that you're going to get a rearrangement, so you get a hydrogen shift, so we call that hydride shift. So that hydrogen will move to that position, and therefore, so we say H minus shift, which will generate a new electrophile, now with a carbocation there, which is secondary carbocation that's more stable. Remember, tertiary carbocation is more stable than secondary, which is much more stable than primary. And because of that, the major product will be the one formed from the secondary carbocation, while the minor product will be the one from the original primary carbocation. And that's going to add to the aromatic ring, because there is no other group, side group on the aromatic ring, so it doesn't matter which carbon on the ring it's going to add to. So that secondary carbocation means the connection will be through that carbon. You end up with that as one product, so that will be the major product. And then you get a minor product through the primary carbocation. Make sure you maintain the number of carbons, 1, 2, 3, and 4, 1, 2, 3, and 4, 1, 2, 3, and 4. Number F. In this reaction, we are using potassium permanganate, which is a strong oxidizing agent. And what it does is that it's going to cut after the first carbon. So that's the alpha carbon, the carbon that's connected to the benzene ring. You cut any other group that comes after that. So you end up with that carbon becoming a carboxylic acid. Next, with NBS, remember NBS reacts like a Br2 with peroxide and say light. Then that's going to be a free radical reaction. And what that does is that it ends up substituting one of these hydrogens at the carbon immediately after the benzene ring, so the alpha carbon. You end up with one of the hydrogen substituted with the bromine while maintaining the other hydrogen. That actually results in bromination, where you add a bromine. Thank you very much for your time. If you enjoyed this presentation, please remember to like this video and also to support the channel by subscribing.